Okay, so here's another practice problem. This is a Newton's third law practice because we've done quite a bit of practice with Newton's second and first laws. But now we're going to need to still use Newton's first and second laws, but we're going to add in Newton's third law as well, which is that statement that for every action, there's an equal but opposite reaction. Or in mathematical terms, force of object 1 exerted on object 2 is equal to negative force of object 2 exerted on object number 1. So here in this scenario, we have a person and they are pushing on a wall and they're pushing with this force of 500 newtons. Now, when they push at 500 newtons, this is the maximum, they're at the maximum static friction. And if we do this situation, we can learn some stuff about everything. And we'll say this is maybe not the maximum static friction for the person, but the actual maximum static friction for the wall. Maybe it's a fairly slidey wall. It's very easy to move along. So this person pushes on this slidey wall, and we reach the maximum static friction for the wall at 500 newtons. And now we have to figure out what is the mass of the person who's doing the pushing. Let's make some assumptions, or I'll give you a little bit more information. Mu k of the wall, we'll call that 0.15, and then mu k, sorry, not mu k, but mu s of the wall, and mu s of the person. Mu s of the wall is 0.15, mu s of the person we'll say is 1.0. So they have shoes on that are very grippy, and they can hold quite a bit of force back, whereas the wall is very slidey. So to do this type of problem, one of the first things we should do is maybe draw a picture. So I'll go ahead and do that for you. Here's a wall, super artistic. Maybe it's one of those fancy brick walls, got some striations in it. And then we have our person. Person has all kinds of fancy stuff too, like an arm, just one, legs, and a head. So I believe that's all you need to be a person. All right, so our objects, there's two of them, right? Object number 1 and object number 2, the person and the wall. And they're going to exert forces on each other through this Newton's second law interaction pair of forces. But the question is, what forces are all acting in this picture? I'm going to tell you, in the y direction, of course, each thing is going to have a gravity force and a normal force. But what about in the x direction? It might be a little bit more complicated than you think. So let's go ahead and make a list of the forces that are acting in the x direction. I will give you a hint. There are 4 of them total. 1, 2, 3, and 4. So go ahead and try to figure out what those 4 forces are. It'll be 2 acting on each object, 2 on the person, 2 on the wall. And I'll give you a second for that, and we'll come back. Okay, hopefully you figured out, but if not, the answer is on the person. There will be a friction force, which I'll call F sub S person. That'll be our first force. The second force will be a push force, F push. I'll say that it's the first object's push force. We'll call it maybe F push 1. Third force is going to be a static friction force on the wall, and the final force will be a F push force that the wall exerts back on the person, so we'll call it F push 2. Now, Newton's first law says F of 1 on 2 is equal to negative F of 2 on 1, so that should tell us something about these two push forces. They're going to be equal in magnitude, but opposite in direction. However, when I use this F push notation, it doesn't really tell me where these forces go. So we have to really think about this in terms of Newton's laws, because this notation that we have for Newton's laws actually tells us quite a bit of information. Obviously, it tells us stuff about the direction with the negative sign and all kinds of things like that. But the important thing I want to look at is this on 1. So F of 2 on 1 is F of this wall exerting on person 1. So if I draw a free body diagram for this, then F of 2 on 1 will be on object 1, on the person, and F of 1 on 2 will be exerted on the wall, and so it will be on the wall's free body diagram. So let's go ahead and replace these F push 1 and F push 2, and F push 1 is actually the push that person 1 is exerting, and so it is the push, it is the force of object 1 exerted on object 2. And F push 2 is the push that the wall exerts back, and so it is F of 2 on 1. And now when we draw our free body diagrams, we can see that this force, F of 1 on 2, will go on the wall's free body diagram, and this F of 2 on 1 will go on the person's free body diagram. So wall FBD, person FBD. So FBD for free body diagram. All right, I'm going to make some dots here. Here's my first dot. Here's my second dot. And oh, we should actually define a coordinate system for both these. So positive x to the right and positive y to the up. And we'll do the same coordinate system for our free body diagrams. Plus x, plus y. And the next thing that we do is we maybe just label each one of them. We'll say the first one will be the person, and the second one will be the wall. One on the left will be the person. The dot on the right will be for the wall. So we will draw our free body diagrams. I will give you a few moments to go ahead and give that a shot. And when you're done, go ahead and continue. All right. Our free body diagrams, the person will have a upwards pointing normal force, which we'll call M sub P, and it will have a downwards pointing force of gravity, which we'll call Fg sub P. Let me move that Fg thing because it's going to get in the way. Fg sub P. All right, the person who is object 1 is going to have F of 2 on 1 exerted on them. So I'm going to skip over the x direction for the person just now, and we'll go over to the wall side of things. The wall will have a normal force N sub W and a gravitational force of Fg sub W, and those will work out great. We know that the person is pushing on this thing, and it's going to push to the right. And so we'll put our force of push thing here to the right, which we will call F of object 1 on object 2. So object 2 is again the wall. Let's maybe change our notation. So let's say it's the force of the person exerted on the wall. And since it's on the wall, we put it on the wall's free body diagram. We also know that our acceleration is going to be 0 at this point because we're still in static friction. We still haven't reached the maximum static friction, but we are at that very, very edge, this critical point where it switches over from static to kinetic. So we're not actually moving just yet, and that means our friction force, Fk sub W, or sorry, Fs sub W, is going to be in the opposite direction of our Fp on W force, and it will be the same magnitude. At the same time, when the force of the person pushing on the wall is being exerted, the equal but opposite F of wall on person, again, this is on the person, and so it is on the person's free body diagram, that will be exerted in the opposite direction on the other object, and so we'll have a friction force, F sub, well, not good, that's kind of chunky in there. We'll have a second friction force, F sub S, of the person exerted as well in the opposite direction. I know it doesn't show it here very well because my arrows are not the correct size, but assume that the force of the wall, let me shorten that up a tad, that these are equal magnitude. And they have to be equal magnitude, the friction force and the push forces, because if we didn't, one of these objects will begin to accelerate in some direction, and that's not what that doesn't describe the physical situation of 0 acceleration. Okay, so the next thing that we have to do is we have to figure out a couple of things. We're going to have to find out stuff about the normal force for the wall, stuff about the normal force for the person. So maybe the first thing that we should do is make a statement about Newton's first law for the person and for the wall. I'll do that here in blue. My sum of forces in the y direction on the person, that's going to be equal to 0, and the sum of forces in the y direction for the wall also equal to 0, and these are vector equations. Next step would be to pull out all of the y direction stuff, and these are two separate sets of equations. So our FYP is going to be the normal force vector, n sub p, plus the gravity vector on that person, and still equal to 0 vector. Similarly, on the wall, we will have a force person on wall, or nope, sorry, that's the X direction. We will have the force of gravity on the wall plus the normal force of the wall is equal to 0. We go over to our scalar world from our vectors. Let me zoom in on that. Scalar world from our vector world, and that gives us a positive normal force of the person minus the force of gravity acting on the person is equal to 0. And then we also have a force of gravity on the wall is negative, and we add to that the normal force on the wall, and we should get 0 from that as well. Solving these for normal forces, I get normal force on the person is equal to force of gravity on the person, and that would be equal to mass of the person times g. On the other side of the world, I have my normal force on the wall equal to Fg on the wall, and that is equal to the mass of the wall times g. Now I have this statement, or these two statements, about my normal forces for each of the two objects. And that's a great first place to start at. But the next thing that we're going to do is going to require just a little bit more information, or a little bit more thought. So let's go ahead and move over to another page, and let's think about the X direction stuff going on. I'm going to start off on the wall. So my sum of forces in the X direction on the wall is the vector equation, and it should be equal to 0 because we don't have acceleration in any direction for the wall or for the person. The forces that are acting are F of person on the wall, vector, plus the static friction of the wall, vector. And that should give us 0 vector. Plugging in our, thinking about our coordinate system, we said the push on wall is going to be a positive, and the friction would then have to be negative. So we get F of push on wall minus friction, static friction on the wall, is equal to 0 when we go into our scalar equation. On the other side of the world, we have Fx of the person is equal to 0 vector. So go ahead and write out your vector equation and change that over to a scalar equation. I'll give you a second to go ahead and try that out. Okay, continuing on, we would have the F of the wall acting on the person vector plus the static friction of the person vector is equal to 0. And putting in our directional stuff, in the walls world, its push force that it feels is positive, and through Newton's third law, we can see that our F of W on P will be in the negative direction. Our static friction force on that person, F sub SP, will be in the positive direction then. Oops, looks like I drew a vector on top of a scalar. That's not correct. And this is the answer that we're looking for that last check. All right, now we have these two statements. We don't know how to really calculate F of W on P, but we do have a value that we measured, and so that's at 500 newtons. We know one of them is going to be 500, one of them is negative, and that's reflected right here. But the other thing we know is what our friction equation is for the wall. So we are talking about when we've reached this maximum friction for this slidey wall, and now we know that 500 newtons should be equal to that. But just to be sure, let's go ahead and use our Newton's first law to verify that F of P on W is equal to our static friction on the wall, and that would be equal to mu sub s times the normal force on the wall. Going back to the other side, if I, pull up that information about the normal force, we can pretty quickly calculate it. Our normal force is given to us as mg because this is a horizontal surface, and so we'd have mu sub s times normal force of mass of the wall times gravitational acceleration constant. If I do this, I can calculate what my force of push on wall was, but since I know what that is already, and I know mu sub s, there's really not much here to do in this equation. But the important thing that we can see is that this friction is related to this this push force, and they cancel each other out just perfectly, giving us that 0 acceleration. On the other side of the world, we'd have our person stuff, and we can solve this for our F of W on P by adding that F of W on P to both sides and subtract, and flipping the order, I guess. So we'll say force of the wall on the person is equal to the friction static force on the person. And that is equal to mu sub s times mass of the person times g. This mass of the person is what we want, right? We're trying to solve for this thing. We know what the force of the wall is, or the force of the push on the wall. That's that F of person on wall. But we know the force of the person on the wall is equal to the force of the wall on the person as far as the magnitude goes. And so what I can now say is that this is known, mu sub s is known, g is always known near Earth, and so we can just do some algebra. But first I'm going to rewrite this equation. So F of wall on person is equal to mu sub s times mass of the person times g. So go ahead and solve this for our variable that we're trying to calculate, and I will give you a second to work on that. Okay, as you recall, we were solving for the mass of the person, so if I divide both sides by mu sub s times g, my mu sub s is cancel, my g's cancel, I'm left with mass of the person, and that would be calculated by the force of the wall on the person divided by mu sub s times g. So this is just equal to the force of the person on the wall divided by mu sub s times g, which we said was 500 newtons. And on the bottom, we have our friction or coefficient of friction. Make sure that you understand this is the coefficient of friction for the person. And so that was somewhere around, I think it was 0.5. Check. Oh, it was 1.0. Ah, okay. So mu sub s is 1.0, g is 10 meters per second squared. If I do this calculation, I should get that the mass of the person is 50 kilograms. There we go. All right, we'll try another one, maybe just one more that will have some interesting stuff happening on it. But I think that'll be about it for today.